Good evening. Welcome to the RSCS member webinar series. I am Kim Hesselbarth, RSCS Marketing Manager. I would like to welcome everyone to tonight's session on Thermography Principles and Applications presented by Bryn C. Cooksey, CMS, RCT. Bryn's presentation will last approximately 45 minutes, and afterwards there will be a Q&A session. Please submit any questions that you have throughout Bryn's presentation using the GoToWebinar dialog box on the right-hand side of your screen. I'll field the questions aloud and ask them to Bryn. Tonight's presentation is being recorded and will be available online for viewing at your convenience as soon as possible. Now I'd like to introduce our presenter for the evening, Bryn Cooksey.
Thank you, Kim. Once again, good evening, everyone. Thank you for joining tonight's webinar. Tonight, we're going to be talking about thermography, principles, and applications. So let's get started. Our objectives for tonight, we're going to have a brief introduction about thermography, the actual science. Then we're going to talk about applied theory, and then we're going to discuss the equipment, the use and handling of the infrared camera, and then consider a couple practical applications. All right. So basically, thermography technology has been used commercially since the 1960s. Before the 1960s, it was used specifically for military applications. The way it works, thermography uses thermal energy as a basis for its operation. And since our industry is in the heating and cooling business, thermography is a valuable asset to our industry. Here's a big picture. When we refer to thermography as a trade practice in a more general definition, we're basically using electronic optical devices to measure and detect infrared radiation, or heat energy. When we want to define it more specifically, when we talk about infrared radiation, we're talking about the transfer of heat via electromagnetic waves. The radiation as measured is then converted into a surface temperature and a thermal image. Right here is a thermal image. This is basically the heat signature produced by an infrared camera of a scroll compressor operating properly. As you may know, with a scroll compressor, relatively low temperature, low pressure refrigerant vapor enters the bottom, and higher temperature, higher pressure vapor is discharged out the top. This thermal imaging camera picture is showing the heat being emitted from the specific object, and that camera assigns a color and temperature value to it. To get on the same page, let's consider some definitions. When we talk about infrared, meaning past red, is a term that we use to describe the specific frequency of electromagnetic radiation. When we talk about thermography, we're referring to a thermal picture. Another definition commonly used is radiometric image. Once that imaging camera produces that thermal picture, now we can apply temperature calculations throughout that picture for evaluation. Unfortunately, the terms are often incorrectly used. So why purchase this equipment? Why bother to sit in this webinar and learn about the science? Well, every product that you purchase, you have to consider your investment versus your value. So your investment is going to involve an initial cost, a reduced initial cost. We'll discuss that further. You also are going to have a cost of ownership. Some infrared cameras may require calibration, depending on the manufacturer. What value would you get out of purchasing a camera or using this technology or science? Well, safety, approach distances, time savings by reducing your downtime for equipment, and then usefulness. You can use this technology or science to help you create maintenance programs or even to find a root cause of a particular problem. Another advantage of thermography testing is that it's considered non-destructive testing. On your screen, you have a lengthy definition of what destructive testing is. However, basically, in simple terms, destructive testing is applying some type of hazardous energy to a component, material, or system to evaluate it. One of the advantages of thermography is that you can evaluate a component, system, or material without applying any energy to it. That makes this a really great advantage. Other types of non-destructive testing that you may encounter might include vibration analysis. One specific benefit from thermography or infrared technology is that you can reduce your electrical hazards. Well, how so? Well, you can inspect equipment without being in direct contact with it, which is pretty important. Most often, using this technology can keep you from shock and arc flash hazards, and you can perform an assessment of your equipment by being outside of an arc flash boundary. The equipment that you see on your screen right now is electrical equipment. On your left is switchgear enclosure, and on your right is an industrial circuit breaker. This circuit breaker may be used for like a large centrifugal chiller or a very large industrial pump. Well, these breakers have been known to fail without any warning. So inspecting them can be extremely dangerous. Using infrared technology, you can view equipment like this from a safe distance without being in the presence of an arc flash hazard. Another huge benefit of thermography is reliability. Time is money. Equipment can be inspected with the equipment in service or running, and this will help you also reduce unplanned equipment outages, which can be costly. Another benefit, data trending. You can use infrared technology and implement it into a preventative or predictive maintenance program. This can help you anticipate failures. You can actually look at a specific piece of equipment or component and get an idea of how close it is to its failure mode. Another benefit, you can perform what's called root cause analysis. Root cause analysis helps you determine why a system or component failed. To get the biggest bang for your buck for this technology or this equipment, it is always going to yield the best results if you use this with a baseline. Quite simply, a baseline means prior to viewing anything with your thermal imaging camera, establish a baseline so that if you make any changes or recommendations, you have a baseline from which you started. Very often this means taking initial readings when a piece of equipment is installed, or if you're doing home performance, taking pictures or a thermal image of the structure market fairly consistently in recent years. And the reason is that we have had a significant drop in price. Significant, as much as 10 times. Older models of thermal imaging cameras cost sometimes as much as $30,000 or $40,000. In fact, they still do. But now we can get comparable models to do all the tests that we need to do for our industry by purchasing one at a fraction of that cost, sometimes less than 10%. This now makes this technology advantageous to use in our industry. So, unlike all good things, there are some limitations. Let's discuss those. One of the first limitations is that the infrared camera can interfere with radio frequencies. That's important to note. Other limitations include that infrared cameras should not be aimed at intense source of energy, such as the sun or devices that emit laser radiation. Some other limitations include that the infrared camera should not be used in very high ambient locations. This specific temperature is going to be dependent on the make and manufacturer of your piece of equipment. Another really important limitation that you should consider: you should not use thermography as acceptance criteria. Basically, we shouldn't use the pictures that we receive from an infrared camera to condemn equipment based on the images. It's accepted best trade practice to gather information using the infrared camera and using some type of secondary method of verifying your assumptions. So we shouldn't use this camera for a no-go or go scenario. Some other limitations include the actual things that we measure. There are things called thermal mirrors that reflect a large portion of infrared radiation that they receive, such as a pipe with a shiny surface, i.e. a copper pipe. If we were to view a copper pipe with an infrared camera, we could get an improper reading. To help counteract that, we can use some type of component such as electrical tape and place that on the component that we're going to measure to reduce that reflection. And we're going to talk about this specifically when we talk about applied theory. Some other limitations include the personnel using the equipment, not the equipment itself. And these are generated by errors. So the camera's usefulness is dependent upon the skill of the user. The reason why is because all materials are not created equal. The user has to understand the term thermal capacitance, or a material's ability to store heat. Some materials reflect a large portion of infrared radiation it receives, such as that copper pipe we just talked about, and they're called thermal mirrors. So basically, the mass that receives the heat is going to reflect more heat than it emits. And we'll talk about those terms here in a little while. Once again, the usefulness is going to be limited without a baseline. So without an established baseline, that's going to be your best chance of success. And then lastly, in order to make a complete evaluation, you must evaluate the images thoroughly, looking for hotspots, looking for specific detail to help you gain information. Here's a situation where that might come into play. So this is a fused three-phase disconnect on a 10-ton air conditioner. The specific problem I was having is that the left phase, if you look at your left picture, it seems to be overheating. An initial complaint was no cooling. Well, that left phase or left fuse continued to blow. So upon arrival, after interviewing the customer, I started investigating the equipment. One of the things that can blow a fuse is ground faults, such as in motors or other components. So to identify what ground fault I had, I chose and selected a megameter to see exactly which component inside the air conditioner may be defective. So I mega-ohmed all of my motors, essentially. And I also checked my capacitors and contactors for grounds also. Well, during that investigation, I didn't find any grounds. So I refused the disconnect, re-energized it, and took a thermal picture. Well, upon re-energizing it, I immediately noticed that this left phase was starting to overheat almost instantly. So is this a current imbalance or is this a ground fault? So to continue further, after several minutes of runtime, that same fuse blew. After that same fuse blew, I performed a lockout-tagout procedure, removed the fuses, and I mega-ohmed each of the cables feeding that disconnect to ground. That test confirmed my assumption that I might have had a loose connection or a ground fault. I performed a current and balance test, and that test proved to be everything was in band, within 10% as I expected. Well, when I did the measure ohm test and tested each cable to ground, I determined that that left phase that kept blowing had a really low resistance to ground. And apparently, once the equipment started up and got in service and got to steady state, it would eventually work its way to ground and blow that left phase. So this is a way to use that instrument. It's not a no-go or go acceptance criteria device. It helps you provide information so you can use a secondary method to understand what's going on with your piece of equipment. This particular device that I use also performed a secondary image, not a thermogram, an actual image of what I was looking at just for comparison. If you look closer at the two pictures again, on the left, my target is towards the center and right phase. I'm measuring about 9 degrees Fahrenheit cooler than I am measuring on my left phase. This is the same disconnect from the previous slide. So obviously there's some signs of overheating. If you have a well-balanced system, everything should be pretty much the same temperature. This is a loose fuse clip scenario from a three-phase disconnect that I encountered using another manufacturer's piece of equipment. Just to show you that you shouldn't make assumptions just based on the image that you see. You have to perform a secondary test to verify your assumptions. So what other industries use infrared technology? The military is key. Police and fire departments, the HVAC industry, our industry, and electric power utilities. Building performance professionals. More specifically, if you were to purchase one, what things could you do with this infrared technology? So specific HVAC applications include testing installation effectiveness. That can be installation inside of walls, installation inside of pipes, verifying the installation to see that it's effective. Electrical equipment, like we just showed. Electronics. Airflow diagnostics. Even though ductwork would be a thermal mirror, you would be able to see the air coming out of seams that have not been sealed properly. Another really good use is heat exchanger effectiveness. Refrigerant leak detection. Steam and hot water heating. These are extremely useful for looking at steam traps to verify that they're operating properly. And another branch of our business that is starting to grow fairly rapidly is building envelope testing. These are used pretty frequently in evaluating a building shell. With that, Kim, I'd like to pose the first poll question.
All right, we'll go ahead and get that launched. And that question